Good afternoon, Internet. I am Matt Buyak, and in this video we'll look at a solution for the 23rd problem in the Project Euler problem archive. Now, this problem asks a question about abundant numbers, and you may recall that an abundant number is one whose proper divisors sum to greater than the number itself. For example, 12 is the smallest such number, and its divisors sum to 16. This problem points out that every number greater than some upper bound, 28,123, can be written as the sum of two abundant numbers. And it asks us to find the sum of all positive integers which cannot be written as the sum of two abundant numbers. So this suggests a pretty straightforward approach to this problem. First, we just need to find all abundant numbers less than or equal to our upper bound. And then we can consider each pair of numbers, abundant numbers less than our upper bound, and calculate their sum. Then we just consider each number less than our upper bound. And if we haven't previously noted it as a sum of two abundant numbers, then we conclude that it is not the sum of two abundant numbers and add it to a running total for our solution. So let's get into it. As usual, we'll copy our template directory to make our problem directory. And open our main.cpp. Now, I just finished a series of 3 videos on the prime factorization of positive integers and calculating those factorizations and some important results that we can derive from those factorizations. And so pulling up the code that we wrote for that, one of the things that we implemented was some code to count the number of divisors of an integer. And so we'll make use of that. Our prime factorization class also makes use of the primes class. So that's another thing to keep in mind. OK, so let's include factors.h. And we'll want to make a primes p and a factorization f. OK. Let's see. We will need some indices. Call them I and j. Let's define our upper bound here. Excuse me, u int, minor typo. So let's just check that was 28,123. So 28,120. And I'm going to say 4 so that we can use this as a proper upper bound. That is considering all the numbers up to 28,123. OK. So now let's, we'll also need a data structure to store our abundant numbers. So let's use a vector for that. If you're not familiar with my past videos, a vector acts a lot like an array. The only difference is that a vector will automatically resize as needed. You don't need to know the size of your vector in advance. And we'll call that abundant. OK. So let's start by calculating those abundant numbers. So we're going to say for I is equal to 1, I is less than upper increment I. And then we'll say f dot factor address of p I. You'll recall, again, we implemented 2 different algorithms for factoring an integer. and one of them uses our primes class to improve performance. The second variant here works better if we're factoring many numbers, as in this case. If we're factoring just one large number, then the first version will have better performance. Okay, so we'll factor our number, and then we can say if f dot sum divisors of yeah, it takes no arguments. Let me just check on that. Yes, no arguments. Minus I is greater than I. Abundant dot pushback I. So one point of clarification, you'll see me subtracting I here. That's because our sum divisors code finds the sum of all divisors, including over I itself. And so we need to subtract that out to get the sum over the proper divisors. So that's what I'm doing there. Okay. So that should give us our abundant numbers. Let's just do a quick check. We'll say first abundant number and abundant dot or abundant 0, just like so. Yes, we'll need to build our library. We'll need to change our makefile to link our library. And we'll need to build our solution. Okay. And you can see it correctly identifies 12 as the first abundant number. Great. Okay, so the next thing we need to do is consider all pairs of abundant numbers and note their sum. So let's create an array of Boolean values that we can use for tracking that. We'll just say bool is sum, and that's going to have upper elements. You'll note that this is a global variable, so it will be initialized to 0 without us having to do that explicitly. Okay, so now we can say for I is equal to 0, I is less than abundant dot size increment I. And for j equals 0, j is less than abundant dot size increment j. And then we'll say if abundant I plus abundant j is less than upper Let's actually introduce a couple of temporary variables here. We'll say a1, a2. Then we can just use those here. And here. Then we'll say is sum a1 plus a2 equals true. All right. And now we can iterate over all numbers less than our upper bound and check to see which are not the sum of abundant numbers. And so for that, we'll need sum is going to be our final answer. say for I equals 1, I is less than upper increment I. And then we'll say if not is sum I, then sum plus equals I. Okay. Oh, and I didn't actually print out our results, so that's not going to actually give us the answer. We'll say sum is equal to sum. Okay, so we have an answer now. Before we check to see if it's correct, there are just a few notes that I want to make, things that we might do to improve the performance of our algorithm. And just as a baseline here, let's see what our performance is looking like. Okay, so we're a quarter of a second roughly is where we're at. So one thing you might notice is that we're actually double checking a lot of these pairs. That is, for example, if we're considering the sum of the first abundant number and the last abundant number in our range, we're considering it that both when I is equal to 12 and when j is equal to 12. And so or excuse me, when I is equal to 0 and when j is equal to 0. And so we can actually reduce our search space by saying j is equal to I. So that's the first improvement that we can make. Okay, you can see same answer and almost twice as fast as expected. You'll note that we're still having to check when j and I are equal, and so it's not going to quite double our performance, but it will be close. Okay, so there are a few other improvements we can make. You'll note that if a1 or if 2 times a1 is greater than our upper bound, then we will fail this check every time. And so we'll be doing a lot of looping that we don't really have to do. And so that's another improvement that we can make here. We can say if I is less than abundant dot size and 2 times abundant I is less than upper. Yes, I believe that should be correct. Excuse me, I didn't time it there. Okay, so you can see a little bit better performance. Okay, and then there's one final improvement that we can make, which is to add a similar check in our loop here. We want a1 plus a2 to be less than upper. Once a2 has gotten large enough that their sum is no longer less than upper, there's no reason to check greater values of a2. And so we can add a check here, a1, excuse me, and a1 plus abundant j is less than upper. And then we don't need this check here. Okay, so you can see still the same answer, and now we're down to 90-something milliseconds from our initial solution of 250-ish milliseconds. Okay, so I think that's enough improvement for this problem. Just had to know a few optimizations. And so now let's go ahead and check our solution. So you'll notice, again, our solution is 4,179,871. And according to the archive, that is the correct answer. OK, so thank you for joining me for that problem. As you might expect, the next video will cover problem number 24.